This time I speak about localization again, like 2 weeks ago, but it's on a different problem actually. So I think it was called many-body localization.
Is it independent topic?
Yeah, well it is not independent, but you'll see the connection. Okay. Many-body localization, a simple model. So, well, 2 weeks ago, right, I spoke about random Schrödinger operators and localization, so let me come back to one body. So we looked at the Hamiltonian of the form minus Laplacian plus V omega, where V omega is a random field. I took it to be discrete, right, but you can take continuous models. And we were interested in, the spectral theory. Questions is the spectral theory of H omega, right? So we are especially, in this case, we are interested in a specific question, which was pure point spectrum, or another equivalent way, which is well known from spectral theory, understanding the evolution e to the it h omega, right? The behavior when t goes to infinity, a large time behavior of this, right? Or maybe of this applied to some vector, right? What is happening in this case? So these two questions are well known to be related, right? Of course, it's not strictly equivalent, right? It's not because that you know the spectral measure. Usually what happens is that you can, from results on the group, right, at large time, you can deduce things on the spectrum of H omega. From knowledge of the spectrum of omega, you can deduce something about this, but usually you never have enough information on either sides to discover completely what's happening on the other side, right? Theoretically, of course, it's possible, but usually the information that you can get is not good enough to do it the complete resolution, but things are related, right? And of course, another thing is understanding, well, the function or the family of operators, right? I write them as kernel. These kernels, right? If you understand this kernel perfectly for all values of z, just z non-real, okay? You certainly can recover this, and you can recover the spectrum, right? But as I said, usually it is not perfect because the information that you get on any of these three problems is not good enough to reveal all the information about the other ones, right? You need to know everything to actually know everything about the other ones, right? And so in particular, what we saw last time is that localization was something like, right? So I put quotes because I gave a precise theorem last time. I will not this time for this. Was something like, if you look at e to the it h omega x y, so you look at the semi-group, right? And you can take this, take the sum over the x's. Let's imagine that we are still in ZD, right? I take a model over ZD. I didn't specify it over RD, you can do the same things, but let's say in ZD. And you look at e to the alpha x minus y, and then you take the supremum over y of the expectation of this. This is finite, right? This is a typical statement, right? And sorry, I forgot something. Sorry, here there's something missing. I take a supremum over all time in R, and I take the expectation here, and I take a supremum over y, right? This is finite. This is, actually I gave a more general condition where here this was replaced by a function of the operator, and I assumed that the function was bounded by 1. Okay? And this is localization. That's a criterion for localization, right? So in particular, such a criterion implies that H omega has only eigenvalues and eigenfunctions. So if phi of E is an eigenfunction, it's satisfied that this is going to decay, like some new constant beta, y, right? And here you have a constant phi that depends on phi on omega. Everything here, right, the spectrum itself, the eigenvalues do depend on omega, right? They depend on this random parameter. But you get exponential decay, and the exponent here does not depend on omega, right? So here the statement is there exists alpha, positive, such that one has this. One can prove this from any model.
In one dimension, right?
Not only in one dimension, even in higher dimensions, you can do this. You need to do something else. In higher dimensions,
Yeah,
right?
I speak
Actually, in higher dimensions,
Yes, I speak only about beta.
or the beta, even the beta, you have it in higher dimensions. It is true, but it needs some. What happens is that in higher dimensions,
Is it
for
uniform
example,
in direction?
sorry?
Is it uniform in direction?
Well, you have a constant, you have an upper bound, which is uniform. How it depends on the direction is another question, which is actually not very, the answers to that are not very well known. Okay, so what is the optimal constant here, and how should it depend? This is going to be much more complicated in higher dimension, right? But still, you have something like this. The only thing is that in higher dimension, you will have more stringent conditions on the operator h omega for such a statement, for this statement, the first here, to hold, right? In particular, it will only hold, for example, if you have large randomness, right? Meaning that roughly the variance of this random field needs to be large, right? And if you're in the continuous case, then even this is not enough. You won't know this for all energies. This would apply this for all energies. You won't get this for all energies, but just some part of the spectrum, okay? Okay, so that's just a brief summary. Okay, a very quick summary. But the thing is, what are these models about? What is this one particle Schrödinger operator supposed to modelize? What it is supposed to modelize is just a single particle, right, inside some random medium. So what is a typical random medium? Well, you've all learned, right, that basically crystals are periodic structures, right? But because of defects in nature, in these periodic structures, you have random impurities, right, that happen. The crystals are actually, in true nature, in many cases, the crystals are not perfect. So you have impurities. And what you like to understand is you have a single particle and you'd like to know how it diffuses through this crystal, right? So that's the basic theory of one body. So you imagine that this is your one quantum particle that goes through the crystal, and you'd like to understand how this crystal scatters it, if it does at all. Okay? But the truth is, nature is more complicated than that. If you think of a piece of material, inside this piece, the number of particles is actually very large. It's not one particle. It's many particles that you have inside this crystal, right? I mean, maybe I put them in red, my particles in here. Of course, they are quantum particles, so I should not represent them as dots, right? Because they are quantum, I shouldn't represent them because they are wave functions, so they live everywhere, right? It's just to keep an image, right? They're not classical particles. They're quantum particles. But there are many particles, right? So typically, if you consider a random material like a semiconductor, right? You have, well, inside a small piece of the crystal, due to the Avogadro number, right? You have 10 to the 23 particles per unit of volume, right? 10 to the 23, that's the Avogadro, 6.02 if I remember well, 10 to the 23, right? 2 times 10 to the 23 particles per unit. Well, I don't want to tell you what the unit of volume is, but it is, well, right, per mole actually. It's not a unit of volume, right? So it's a way to measure things. And among these 10 to the 23, of course, most of them actually constitute the crystal, meaning that they don't move. But each atom has some parts of its electrons that can move inside there. For example, this is where electricity comes from. So actually the number of particles inside your medium, right, that can move. For example, when you have a wire, right, an electric wire, or when you have a real semiconductor, if you put some potential, many particles can move. Otherwise, you'd never have an electric current. You have a single particle moving, right? This carries too little energy to be doing anything useful, right? You need some stream of particles. So you have a huge number of particles in there. This is why considering one-body problems is not enough. What you should look at is many-body problems. Many-body. What does it mean? It means that you take your random Hamiltonian, right? Cut it over some box. Let me take this in ZD, right? I'll work on a one-dimensional real line model later on, but for the moment, as I only spoke about discrete models, let's keep it discrete, okay? You take this Hamiltonian, so that's for one body, okay? Well, and you have many particles, which means that, well, all the particles you consider at first to be identical, right? There is no difference between one electron and another one. So the first electron will be subjected, right, to the Hamiltonian for the first electron, right? And then the second electron is going to be subjected to the same Hamiltonian. So this is the identity over lambda, right? I write it just one, but 1 here is 1 over lambda, right? And so on. Well, not exactly, because the number of particles inside, actually, if you consider all the atoms that are contributing here, not all of them will actually contribute a particle, right? So the density, actually, the density of particle, the number of particles among these 10 to the 23 will, this is physical measurements, right, be more of the size, well, 10 to the 15, 10 to the 17, right? Which means that the ratio, and this is what is going to be the important thing, the ratio of the number of particles to the volume is going to be 10 to the minus 6, 10 to the minus 7. There are actually few particles that can move around. It's not that you move the whole crystal, right? So, but I'll be coming to that in a second. So you have n. So of course, and you have n particles, you have n here, right? This is the n. Actually, let me call it large n. Large n. Okay? And these are free particles. These are free particles, meaning you see each particle lives independently from another, right? Because all these Hamiltonians commute, they are just equivalent, unitarily equivalent to a single particle Hamiltonian, right? And there was one thing missing here, right? There's one thing missing here is what people call the particle type, right? What does it mean? It means that you have this Hamiltonian, right? But as a mathematician, well, giving this formula is not enough to define an operator. You need a space on which to operate, right? You need a space. So one space would be just to take the tensor product, the direct tensor product of L2 lambda, right? So this would be what is his name now? I can't remember. No, okay, let me call this one H0, right? That's the, just each particle, they're independent of one another, right? And there's no symmetry. But these are not, this is not the natural space one should consider, because particles, they are independent, but they satisfy some symmetry. And there are two symmetries, right? Essentially two symmetries. There are fermions, or Fermi-Dirac symmetry, and there are bosons. And if you consider the Fermi-Dirac symmetry, right, this is, you should consider H Fermi to be the exterior tensor product. This is over n terms. So this is over n terms as well. So you only consider functions, right, when you have this operator acting only on functions that are anti-symmetric, right? And there is the other symmetry, which is the Bosonic symmetry, where you consider the symmetric tensor product of n times L2 lambda. So what does it mean? This means here that if you take This means it's just the functions psi belonging to the symmetric tensor product of lambda, right? N, such that if you take psi of x sigma, this is -1, so this is Fermi, -1, so it is the signature of your permutation of psi of x, where x, or let me call it x bar is x1 to xn, and x sigma bar, and this is for all sigma in the n-fold permutation group, and x sigma bar is nothing but x of sigma 1, x of sigma n, when sigma is some permutation of 1n. Right? Oops. Looks like I lost something. Yeah, I guess I'll fix that. Yep, here we are. I'm going to shorten this. Okay, right, and of course the other one, it's the same definition except that psi x sigma bar is equal to psi x bar. Right, and this is of course valid for any x. Okay, yes, that satisfies this symmetry. And so the case we will be interested in is the fermionic case. So I will consider this operator, right? I will consider this operator. So let me give a name to this thing. H0n omega lambda, right? I already got 4 indices. So I consider H0, so I'm letting you take an H straight. And as I keep the H round for spaces, H straight 0 n omega lambda, right, on, well, the exterior tensor product of L2 lambda, right? So lambda here is some domain in ZD, but actually usually I think of it as a cube, right? I could take any domain, but I think of it as a cube. Okay. And, well, this is not all, because the main effect comes from the following. The particles are interacting. Right? This is where the main new effect comes from. As I said, imagine that you would have only H0, then these operators all commute, but we know that the spectral theory of commuting operators is actually given explicitly by the spectra of each of the individual operators, right? And you know completely, I'll come back to this in the fermionic case, but you know completely what the spectral operator or the spectral theory of this is, knowing the one of H omega lambda. Okay? So what really complicates matters and makes it actually not only an interesting mathematical problem, but also an interesting physical problem, which is far from being totally understood, from being solved, is interactions. So let's speak about the interactions. Particles are interacting. Let's make it just simple. Imagine that these are electrons, right? And they are just interacting pairwise, meaning that 2 electrons, right? Well, as they are particles having the same sign, they are going to repel from one another, right? They won't be attracted. They have the same charge. They will be repelled from one another. So what does it mean? It means that you should consider W of x bar, which is the sum of U of xi minus xj for I less than j. And U is going to be some function from ZD to R plus, right? From ZD to R plus. That is non-negative, right? Because the 2 particles are repelling each other, right? They don't want to be close together. So it means that they're getting pushed apart from one another, which means that you should put a positive potential here, right? Because this one is going to have a force, a gradient, which pushes them apart, right? And the operator you should consider, so this is Wn. So x bar is as before, x1 to xn, right? And you should consider HUN omega lambda, which is H0n omega lambda plus Wn of x bar. Right? That's the operator you are interested in. And of course, it is a complicated object, right? Because n is large, and lambda is large. In nature, there are no infinite crystals, right? I mean, if you're in the lab, crystals are always finite, but because they contain many components, right? The distance, the interatomic distance of the crystal is of the size of the angstrom, right? So there are many components. You can consider what is called the thermodynamic limit. Which means that you let lambda go to infinity, right? The volume of lambda grows. You let n, the number of particles, go to infinity. And you assume that the ratio, number of particles divided by volume, converges to some constant rho, which is positive, which of course is called the density of particles. Right? This is what is called the thermodynamic limit. So you consider the new material, you have a large chunk of material which contains a number of particles which is roughly proportional to the volume of the material, right? And which is of size, which is equal, if you want, to rho. Okay? And typically, as I said, rho is a positive fixed number, but it is a small number, right? In most of the real materials, the proportion of the number of electrons that are actually moving inside the material is much smaller than the total number of available electrons and the total number of atoms inside there, right? So rho is a small number. As I told before, exactly. So it's order 10 to the minus 6, 10 to the minus 7, around these things. Right, in physical materials. But nevertheless, you see that this is going to be a difficult mathematical problem, right? Because you have this limit, right? You already know that the spectral theory, what you can say about the spectral theory of an operator, if you take dimension 3, right? So this is in dimension d, but okay, then take dimension d equal 3, it's already complicated, right? There are no really effective tools to do complete computations, right? So this is going to be a difficult problem. So, well, the only way to solve difficult problems is to try to ask rather simple questions, right? So knowing the whole spectral theory of such a thing is just a nightmare, right? I mean, it's just no way to understand. And too many things can happen, actually. It's too big. But we can ask simple questions.
You need to know some macro characteristics, right?
Some?
So you need to know some macro characteristics.
Yeah, you need to know macroscopic characteristics, but the problem is there are too many states, right? You see, if you take the problem is you need to ask the question about the right object, right? Because there are too many objects inside this thing, too many possibilities, right? I mean, imagine, right? Lambda is a finite volume, right? So it is in dimension, let's say it is 0 to, I don't know, L, right, to the D, okay? Then the dimension, so this is just a huge matrix. This thing is just a huge matrix, right? The problem is that the size of this matrix is L to the D to the power, what did I say? N, so it is L to the D divided by rho, right? That's the size of this matrix, right? So it's e to the log L, right? That's the dimension of the matrix, and you want to know what's happening for this matrix when L gets large, right? And the matrix is quite complicated, right? It's full of interactions because of this term, right? Because of these terms, it tells you that dimensions, every dimension in there, in this matrix, is connected to the other one. Even if it's in a simple way, it's still quite complicated.
The matrix is not random.
Oh, it is random, but okay, you can fix a random thing. You can even if you don't take it to be random, it's going to be interesting. Okay, it's going to be interesting, and there are some things known for the free Laplacian, for example, but many things are not known, actually, right? Most of the things are not known. Okay, so
I mean, the interaction is random also.
The what? No, the interaction is not random. This is not random. What is random is the medium, right? Where everybody is living. The interaction, you could also take random interaction, but it doesn't make much sense because interaction between elementary particles is not a random thing. It's more that your crystal you're looking at is some sample, right, of some material that is natural to consider random. And so what is the basic question you want to ask for, right? So one of the simplest questions, right, is, well, what is happening to the ground state, right? Because this is, in the end, when you let time evolve, right, this is the state into which everything should relax, right? So of course, it's more complicated than that, right? Because we have a finite crystal. We send the size of the crystal to infinity, the number of particles in there to infinity, and if you look at time scales, you should also send time to infinity, and all together, right? In a way which is, it's non-trivial how to take this triple limit in a way that makes sense, right? So of course, what is, if you take the limit time to infinity for fixed lambda and L, what you get is that the things will relax to the ground state, right? You can look at the ground state of this operator. So one question would be, what does the ground state of H U n omega lambda look like? Right? What does it look like when you switch on the interaction? So the ground state is easy to define. You have a big matrix, right? But it's still a finite dimensional matrix. It's big, finite dimensional. You can look at the infimum of the spectrum, right? You can assume that, you look at this one, right? Let's assume, so this is a matrix, right? It has an infimum of a spectrum. So of course the infimum of this sum is going to be n times, actually not in this case because of the anti-symmetry, right? It's going to be the sum, we're going to come to that. It's going to be the sum of the n first eigenvalues of this one, which is something, has a finite value, right? And you add some potential, which is non-negative, so the infimum is going to be above this value, right? And it's a good question to ask what's happening to the infimum of the spectrum. What does this vector look like, right? But remember, the question I'm asking, I'm having something in the back of my head. The question I'm basically asking, or the phenomenon I'm after is the following. Without the interaction, we know that the eigenvalues of H omega are localized, meaning that they are nicely exponentially decaying vectors, right? In particular, the infimum of the spectrums, nicely exponentially decaying vectors, right? And the question is, does such a behavior survive when you have interacting particles and you switch on an interaction? Are particles still localized, right? And where is the difficulty of this question? Well, difficulty is the following, is that such an estimate doesn't make sense anymore, right? You can look, you could imagine, this is a finite dimensional matrix. I can look at e to the h omega, I can replace this operator by this one. The only thing that happens is that x and y are going to be in much larger spaces, right? They are going into be in a space of dimensions this thing. Okay, so they're going to be in dimension, much larger dimension, but still such an expression makes perfectly sense. Okay? The problem is the following. If you think of my picture here, you have this volume where you have your random thing. I draw a grid right? I draw a grid, but it's not a grid, it's random, okay? And you have these many particles in there. Even if there are only a small density, the particles are still living almost everywhere. So you cannot really expect that the things are decaying in the way I say here, right? Because there are many particles. The number of particles inside your crystal is proportional. It's proportional to the size of the crystal. So the particles are everywhere. Okay, so you cannot expect a spatial decay of the kind I'm writing up here. Right? Because there are particles more or less everywhere in the crystal. The typical distance between two particles, right, should be something like, well, you look at the volume and divide by the density, right? You have just space, because you have to put so many particles in there, so you have just some space around each particle. So that's one of the basic first things you can say, is that the questions, phrasing it in this term, is not exactly the right way to look at it. And actually, physicists have thought about it actually a lot of time, and they're still not completely agreeing with each other what the right definition should be, right? Of how do you define localization. So in such medium, actually there are many definitions, right? And it's not clear that they're all equivalent to one another. I mean, from the physicist, mathematically there are only very few works on this, right? But even from physicists' point of view, it's not completely obvious that all the definitions that they give for localizations, right, what they call a criterion, which mainly is, how do they justify these for being criteria? They use numerical experiments, right? And some actually true life experiments, right? They're now able to do some true life experiments, of course not with too many particles, but still. And the criteria that they have, they don't know whether they're all equivalent, right? Whether they give you a single definition of what localization is, but have various criteria that were proposed. And maybe the one thing we should look at, right, is that if something should be localized, right, if something should be localized, it should be a system without interactions, because all the particles are localized. So the system without interactions should be localized, right? This one should satisfy a criterion that one can call localization. Okay? So what happens when U is not there, when U vanishes identically, right? Then we know what the spectrum of H omega lambda 0 n is, right? We know exactly what it is. Well, imagine that E1 of omega lambda, sorry, let me call it little e, En of omega lambda, or Ek, are the eigenvalues of H omega restricted to lambda, and phi 1 are the eigenvectors associated to these eigenvalues, right? So we know that this is a matrix. This operator here is just a matrix. So it has eigenvalues and eigenvectors. Well, as I consider it maybe an operator on the real line, it may have infinitely many of them, right? I also want to consider operators on the real line, but we can imagine that it has only finitely many of them. Well, then we know that actually what are the eigenvalues of this one? It is just EJ1, right? Well, I write it EJ1, but I forget about the omega and lambda, just to shorten notations. Plus EJ2 plus EJN, right? For J1 less than J2 larger than 1, strictly less than Jn. So I assume that the eigenvalues here, are repeated according to multiplicity, right? I repeat them according to multiplicity. They're just this. So these are just multi-indices. And the associated eigenvalue is just phi j1 exterior phi jn. Right? It's just the Slater determinant. These are the eigenfunctions, right? So the spectrum of this one is completely known just by algebraic properties of the operator, right? It comes from the fact that these vectors are obviously eigenvectors of this operator, right? Associated to this eigenvalue. And it is easy to check that these vectors form an orthonormal basis of this space. Right? So let me just remind you what this Slater determinant is. It is just at the point x bar, it is just equal to the determinant of the matrix phi j1 x1, phi j1 xn, phi jn x1, phi jn xn, right? And normalized properly 1 over square root of n factorial. Right? You have to normalize this properly, not property. Right? This is just the Slater determinant. And form, so you know explicitly what the eigenvalues and eigenvectors of these things are. So how much am I doing time-wise?
Okay. You can make a break and say 5, 6, 7.
Okay, I'll make a break soon, actually. I'll make a break. So in particular, what this tells you is that the ground state, so E0, the ground state of n, what did I put? 0 here. E1, the ground state of E of, and here I put 0, lambda, n, omega. So this is the ground state energy of what? Of H0 n omega lambda, right, is equal to E1 plus En. Right? It's the first eigenvalue. It's the smallest sum that you have in here.
But all the Hamiltonians are the same. So the eigenvalue say E1, A2,
No, they are not the same. These are not the same. Because why? Because otherwise this exterior product is 0. You take the first n eigenvalues, right?
Okay.
Some of them may be the same in there because such an eigenvalue has multiplicity.
Okay.
They may all be the same actually. Okay. But when n gets large, because this one stays fixed, right? They are not going to stay the same.
Okay.
Right? And you know that the eigenvector is just phi 1 wedge phi n. So the first thing, the other remark that you can make here is that it's not obvious that the second eigenvalue is not the same as this one, because as soon as you look, if in this sequel you have eigenvalues with multiplicity, right, you see that you can form eigenvalues that are the same here associated to distinct eigenvectors, right? Imagine that you have E1, right? We know that usually for the Schrödinger operator, E1 and E2 are not the same. But imagine that E2 and E3 are the same, right? So if you have only two particles, or imagine that En and En plus 1 are the same, right? It happens that for this n, En and En plus 1 are the same. Then you have this eigenvalue, which is also equal to the one to this one, right? You have two eigenvalues that are the same, these two, in this assumption. And you don't have, and then you don't have simple ground state. So the ground state is not always simple for just symmetric reasons.
And even in the case when there is no interaction, you have a trivial problem of computing the most probable eigenvalues.
Well, this you can compute actually what this I show you how to compute this in a second. Okay, I show you how to compute what happens when n is large for this one. Okay, so you see that you have a twofold problem. So one of the problems is that if you consider the thermodynamic limit, you are leaving the realm of functions, meaning that this thing is a function in more and more variables. So it's not a function. In the end, when you take the limit, it's not a function anymore. It's going what is called the field. Right? The function depends here on finite, so it's a function over an infinite dimensional space. But this is something pretty classical in probability theory, right? If you have a measure on an infinite dimensional space, well, what you do is you study the marginals of the measure, right? Here you do the same kind of things. You study what is called the k-particle, well, the reduced k-particle density matrix, right? Because you want to get rid of this problem that the number of variables in there increases when n goes to infinity, right? You introduce the following thing, k-particle density matrix, which is the analog of marginals for probability measures. So what is it? It's just the following thing. Imagine I take a psi, a vector, in L2 lambda, right? And let's assume that psi, it's not really important, but let's assume that psi is normalized. Right, so take the L2 norm over there, it's normalized to 1. It's not really important, but... And then I say that gamma k of psi, its k-fold density matrix, is not going to be a vector anymore. It's going to be an operator, right? But what is it? It's actually also called gamma k of the operator. So this is the operator projector on psi, right? Which is also, this is the mathematical notation. The physical notation would be this, right? And what you do is you do the following thing. You take the operator psi x1 xn bar, or let's say you take x1 xn, nothing, right? You take psi bar of y1 yn, right? So that's the kernel of this projector. This is a projector, a one-dimensional projector, right? That's the kernel in the operator sense kernel of a one-dimensional projector on psi, not on psi, but on psi, in this space, right? And what you do is you integrate this dy z k plus 1 dz n, where the integral is taken on what? On xk plus 1 equals yk plus 1 equals zk plus 1 integrate over lambda. So you mean that you take xk plus 1 to be equal to yk plus 1 to be equal to this, and you integrate over zk, right? And this for all k. J for all j between k plus 1 and n. So if you want, I'm going to rewrite it below. It's exactly the integral over lambda to the n minus k, right, of psi x1 x2, xk, sorry, z bar, psi y1 yk, z bar, dz bar, where z bar belongs to this. Right, and I forgot, of course, the complex conjugation here. Right? And the usual normalization that you put in front, so this is just a normalization, it's k, no, it's not this, it's n choose k, sorry. The usual normalization is n choose k. So it's clear to see that actually, so of course the sums in the discrete case, the integrals in discrete case are sums, right? And what is clear is that this is, So this is gamma k of psi. And what is clear is that gamma k of psi, well, this projector is a positive operator. It's a rank 1 projector onto psi. So these things are positive operators. When you integrate along k, dz, what you get is a positive operator. Right? Moreover, this is rank 1. So you integrate over finite dimensional space, right? Over finite space, not finite dimensional, but a finite space. So you're going to get a trace class operator, right? This is trace class, right? And you have that because of the normalization factor, the trace of gamma k psi is exactly going to be, the trace of this one is going to be 1 because of my normalization here. And this is going to be n choose k. What is n choose k? Is the number of packets of k particles you can form out of n particles, right? This is one normalize it in this way. It's just a normalization. Okay, so maybe before I do a break, I just finish by saying, so if you consider, so I will essentially only consider two things. I consider gamma 1 of psi and gamma 2. Right? I take two particles, take the 2 particle density matrix and the 1 particle density matrix, right? And imagine that psi is exactly what I have above there. Phi 1, phi n. Then you can check that gamma 1 of psi, is just equal to the sum exactly from 1 to n. Okay? So it is just, if you think of the initial operator we started with, from minus infinity to E n of h omega lambda. Right? This is a simple computation. You plug in the determinant, right? The explicit formula that we have, and you perform the computation. And so let me call, okay. So let me call this pi, just pi omega n. I forget about h, right? To just call it pi omega n. And if you compute gamma 2 for the same psi, what you get is the following. It's the sum for j less than k of, the kernel is the following. It's phi j. So this time it's going to be a kernel x1, x2, y1, y2, right? 2 variables left, right? It's a 2 particle density. So you get x1 phi j x2. So this is the determinant. Phi j, phi k x1, phi k x2. Phi j y1, phi j y2, phi k, sorry, y1, phi k y2. Right? You can compute it explicitly in this case. You can compute the case one as well. And you can rewrite it, if you expand it, you can rewrite it as pi omega. So this is a kernel, right, in xy. Right, that's the kernel of this projector. You can rewrite it as pi x1 y1 pi omega x2 y2 minus pi omega x1 y2 pi omega x2 y1. Just do the expansion, right, of the determinants, and you see that what you get is this.